So we have this limit as delta x goes to 0, f of x plus delta x minus f of x all over delta x. That is our definition of the slope of the tangent line. There is another phrase we call this. There's another piece of terminology which also applies to this expression. It's called the derivative. The phrase, the derivative, means that limit, if it exists, right? If this limit exists. If the limit does not exist, then we say the slope of the tangent line does not exist. That tangent line does not have a slope. If the limit does not exist, then we say the derivative does not exist. The phrase, the derivative, that limit, and the phrase, the slope of the tangent line, they all mean the same thing. From this point forward, anytime we say the derivative, what we mean is that limit, if it exists. And the phrase, the derivative, and the phrase, the slope of the tangent line, for our purposes, are essentially interchangeable. If you are asked to find the slope of the tangent line, that's the same thing as being asked to find the derivative. And that computation is this expression. This expression finds the derivative, which is the same thing as the slope of the tangent line. Anytime you find the derivative, no matter what other interpretation it might have, it also carries with it the interpretation, the slope of the tangent line. Each of these three pieces has exactly the same meaning. So from this point forward, these are considered to be interchangeable. When, not if, when you are asked to find the slope of the tangent line, that's the same thing as being asked to find the derivative. When you find the derivative, one of the possible interpretations, it turns out there will be more. There will be more interpretations than just this. But at least this, in addition to whatever other interpretation you have, the phrase, the derivative, and the phrase, the slope of the tangent line, are interchangeable. Now, the notation that we use, anytime we introduce a new concept in mathematics, we have the notation. All right, so here's our new notation. If f of x, or let's say, if y equals f of x is the function at issue, all right? If y equals f of x is the function we're discussing, then we use these notations. We may write f with a little, it's like an apostrophe. You read this as f prime. Read this as f prime. F with a little slash, a little apostrophe looking mark. You read this as f prime. This is considered to be the derivative. So typically we would write f prime is equal to the limit as delta x goes to 0 of, and so on, so on, so on. So that collection of symbols means this expression. Another way to write this is this. You'll see this symbol. dy divided by dx. dy divided by dx. Except that's not the way you say it. You say this as, you pronounce this, dy dx. You simply say dy dx. Or sometimes you'll say this. We'll say this. The derivative, this is a little more formal, derivative of y with respect to x. The derivative of y with respect to x. The derivative of y with respect to x. What this means, when we write this symbol, there actually is information contained just in the writing of the symbols. When we write this, we mean this y represents this y, and this x represents this x. So in this expression, x is, the technical word is the independent variable. The independent variable, whereas y is considered to be the dependent variable. So this is the dependent variable, this is the independent variable. And so we may write dy divided by dx. So typically we don't say all this verbiage, derivative of y with respect to x. Typically we simply say dy dx, and you don't even utter something for the division sign, it's just simply dy dx. This is very common when you study later on in just a little bit. We're going to talk about what are called related rates. And when we talk about related rates, this is the common notation that gets used. If any of you have differential equations in your future, you'll be using this notation quite a bit. So I will freely choose, I will freely go back and forth between these various notations. F prime of x, dy dx. Sometimes you'll see simply y prime. So instead of f of x equals 3x plus 7, we could write y equals 3x plus 7. And instead of writing f prime equals the derivative of that function, we could write y prime is the derivative of that function. And of course, this you pronounce this simply y prime. So this little mark here is read prime. Y prime, f prime, y prime. All right? Let's see some other notations. Sometimes you'll see this. This is a little more formal, and we'll use this in certain settings quite a bit. You simply read this as the derivative of f of x. The derivative of f of x. Now again, you could say this is with respect to x. And very often you'll simply say this phrase, d by dx of f of x. D by dx. This symbol, these symbols are read as d by dx. So we have d by dx, it's related to this, d by dx, but this is used to say, I want the derivative of f of x. You could simply read this as the derivative. You could simply read this as the derivative. You could simply read this as the derivative. The derivative. Each of these simply means the derivative. And the only what you put into the brackets, this is the function whose derivative is being evaluated. So we want to find the derivative of this function. You typically don't see this notation stand alone by itself. You will very often see this notation stand alone by itself, or this, or this. You rarely see this stand by itself. This is used as an operation indicator, an operator in a sense. If you study operator theory, this is used as an operation to be formed on, and then you would put a particular function in here. It might be x squared plus 1. So you might see something like this. This is d by dx of x squared plus 1. So that's the way that would typically be read. Another, another notation that you typically see, this has links if you go to Calculus 3. This is called the big D notation. Sometimes you'll see D subscript X. It's called the big D notation. Sometimes in Calc 3 you'll see F sub X. And so again, those all mean the derivative. We will see these two we will not deal much with this semester. These are in your future if you hang around the coursework long enough. We'll see this quite a bit, and then these three will be all over the place. So you should get very used to, very adept at being able to work through and using each of these symbols to represent the derivative. So let's see if we can actually do a real actual problem here. By golly, it's your very first derivative. All right, so we're going to use the definition of f prime of x. We're going to use the definition of the derivative to find the derivative of f of x is equal to, and I have a little function here I'm going to play with. I'm going to say this is x squared minus 4x plus 7. And let's do this. Let's find the derivative. And then let's find the slope. I'm sorry, not the slope. Let's find the equation. Find the equation of the tangent line when x equals, and I'll just pick a number out of the blue sky. Let's make it easy, when x equals 1. So we're given x equals 1, and we want to find the equation of the tangent line. All right? So let's kind of take a look at what's going to happen here in the big picture, and then we'll get into the details. First thing, we're just asked to find the derivative. That's wonderful. And the next piece is, let's find the equation of the tangent line. So the idea is this. We can see this is a parabola, and it's not too challenging to see that this parabola, the vertex is at x equals 2. And so this function looks something like this. The specific details aren't important. Here's 1. X equals 1, we're given that, which means we're given this particular point on that parabola. And we're asked to find the equation of the tangent line. So let's get this blue line here. It's not like we're playing hockey. So that is our tangent line. We need to find the equation of the tangent line. Now, first off, we're going to find the derivative. Then we'll play this game of find the equation of the tangent line. All right? So I'm going to, for part A, I'm going to erase my picture and steal some space back, and then we'll see if we can come back and find, do part B. So part A, we need to find the derivative. Well, we know what f prime of x is. Let's stop here and make sure we have this little detail ironed out. Some of you may have been in a calculus course of some sort before now. And we will, over the course of the next couple sections, the rest of this chapter, we will find some rules which allow us to compute the derivative in a more efficient manner in some cases. Until that time comes, and even after that time comes, it is important for you to be able to find the derivative of a function using the definition, not using the rules. What students like to call them are the shortcut rules. That's not really a very good name. What really they represent are procedures or theorems, actually. But there are rules for evaluating derivatives in a more efficient fashion. I will give you, they are more efficient than going all the way back to the definition. We saw that when we did limits. When we do the limits, very often, at the core base idea are the deltas, the epsilons. But once you understand that principle, then we go beyond that and find some rules for how do you evaluate a limit. Rather than go back to the delta epsilon expression, we can use those rules to evaluate the limit. Well, the same thing's going to happen here. We have this derivative definition. The definition is the limit of that difference quotient, is the limit as delta x goes to 0. F of x plus delta x minus f of x, all divide by delta x. You need to know how to use that procedure. There will come a time this semester when we will encounter a variety of functions. There's going to be a class of functions where none of the sort of more efficient rules we use. We're going to develop rules for all sorts of functions. They will not work on this new class of functions we're going to consider. The only game in town is to go back to the definition. And so I say all that for the following. If the directions say use the definition to find the derivative, then what you must do is use the definition to find the derivative. If you do not use the definition to find the derivative, then you are not going to get full credit out of me. When I ask you to use the definition to find the derivative, I don't care about the final answer. The final result is something about which I don't care. If all you do, and I've had students in the past do this, use the definition to find the derivative. If all you do is write out the final answer, I don't care. What I do care about, and what is important, and what should be part of your skill set, is the ability to use the definition to find the derivative. You need to be able to do that. And you need to be able to do that fairly readily. There may be some, bumps in the road here and there. But that procedure needs to become part of your skill set. And if it doesn't, there are going to come places in the calculus where you are not going to know what to do. You're not going to be able to handle things because you're not able to use the definition to find the derivative. So all that said, you need to be able to do part A. Use the definition. The definition is this: limit as delta x goes to 0, f of x plus delta x minus f of x all over delta x. And then we start to substitute. The limit is delta x goes to 0 of f of something is something squared minus 4 times the something plus 7. So this is familiar from our work in limits back in chapter 1. So this is x plus delta x quantity squared minus 4 times x plus delta x. I'm computing f of x plus delta x plus 7. Minus, and when you subtract a function, whenever you subtract a function, you must subtract with parentheses. Whenever you subtract a function, you should subtract with parentheses. This is x squared minus 4x plus 7. All great big honking over delta x. And I'm going to run out of space unless I'm careful. So I'm going to steal some space because this is back to that problem where it expands out like an accordion. And then every term that does not have delta x needs to cancel out. And it comes back in. So let's see if we can make that happen. This is the limit. This is equal to the limit. Remember, you stop writing LIM when you actually substitute delta x in. But we need to do some arithmetic. I'm sorry, do some algebra and then simplify and try again. So this is the limit as delta x goes to 0 of, when you multiply this out, this is not. This is not x squared plus delta x squared. It is x squared plus 2x delta x. You just go off to the side, FOIL, and bring it back in. Remember, this is a single letter. This is regarded as a single letter. All right? So we've squared that. Minus, distribute the negative 4, the negative with it, minus 4 delta x. And then plus 7. Distribute the negative sign. All great big honking over delta x. All right, let me check all my work here. We're all good to go. Now, at this stage of the game, any term that does not have a delta x should cancel out. So see, we make that there's an x squared and there's a negative x squared. There is a negative 4x and there is a positive 4x. Positive 7, negative 7. So what we're left with is 2x delta x plus delta x quantity squared, what's left, minus 4 delta x all over delta x. Now, once again, factor and cancel the delta x's. Factor out the delta x. Anything left has to have a delta x in it. So this is equal to the limit as delta x goes to 0. Factor out the delta x, leaving behind 2x plus delta x minus 4 all over delta x. And now that cancels with that. Now what are we left with? This is equal to the limit. Delta x goes to 0. What we're left with? 2x plus delta x minus 4. As delta x goes to 0, at long last, we're actually going to substitute delta x equals 0. That's when we stop writing the limit expression. And so this is equal to 2x plus 0 minus 4, which simplifies 2x minus 4. Couldn't be simpler. If you are asked to use the definition to find the derivative, that is what I'm asking you to do. I am not asking you to say this is equal to that and skip over all this work, because I want to know, do you know how to work through this? That is the point. It's not like I woke up today and thought, gee, I wonder what the derivative of x squared minus 4x plus 7 is. How about if I give it to my students and see if they can help me out? That's not what happened. I'm asking you to find the derivative because I want to know if you know how to use the definition. Okay, so all that. This is our final result. So what did we just do? We just found that function f prime of x. And here's the bit. So our answer, excuse me, our answer to part A is the derivative is equal to 2x minus 4. All the x values that work, all the x values that are in the domain of this function, for all the x values in the domain of that function, this is a function of x. The derivative is a function of x in exactly the same manner that the original function is a function of x. If this had been, now there's nothing magic about x. If this is f of t is equal to t squared minus 4t, then everywhere you see an x, there would be a t, and then f prime of t is equal to 2t. The specific letter you pick is not the important factor. What matters is that if you have this function, use the derivative, and you should be able to use the definition of the derivative. This is a function of x. It is the derivative of this. So from f, we can compute f prime of x. All right? Now, what I'm going to do next is, erase all this, we'll do part B. We want to find the equation of the tangent line when x equals 1. All right? So let's see how that works. Part B. Let's go back to our picture here. And there's my tangent line. This is a very badly drawn picture, but you get the idea. Here's x equals 1. And so the coordinates of that point are 1, comma, don't know yet. Now we need that because anytime you're asked to find the equation of any line, let's recall what we need. We need y minus y0 is equal to slope times x minus x0, where x0 and y0 are the coordinates of a specific point that is known to lie on the line. The only point we know that lies on the line is 1, comma, don't know yet. So how do you find the don't know yet? The way you find this y coordinate is you take this value 1 and evaluate the function. If you're given a point in the domain, you just substitute in and find the y value. So, very often, you will simply be given the x coordinate as we were here, right? Here, we're given x equals 1. You'll be given the x coordinate. You will be expected to find the y coordinate. The function finds the coordinates. The derivative finds the slope. The function finds the coordinates. The derivative finds the slope. And so we have the coordinates of the x value. That's the 1. So this value goes here. We're going to find that number, and it's going to go over here in that spot. All right? Well, how do you find that? Well, that we know what the y value is. We know f of, what's my number, 1, is given by, use the original function, that's 1 squared minus 4 times 1 plus 7. That's 1 minus 4 plus 7. That looks like 4 to me. And so the coordinates of this point are 1, 4. And now we know that number, now we know that number. So far we have y minus, that's the 4 we just found, is equal to, don't know yet, x minus, that was the 1 we were given. All right, so far we have the 4 and the 1. And now we need to find the slope. We need the slope of the tangent line. The phrase slope of the tangent line is interchangeable with the phrase the derivative, which we just found. The slope of the tangent line is the derivative of the function. Now the problem is the derivative isn't, we want a specific number. How do we know which number to select? Well, see, that's the key. This is the slope of the tangent line for this parabola. And depending upon which x value we choose, the slope of that tangent line will be different. Here, there's the slope. Here, there's the slope. Here, there's the slope. And so the slope of that tangent line changes depending upon which value we choose. We want the specific tangent line. That is, when x equals 1, we want this specific blue tangent line. And so we need the slope we need the slope evaluated when x equals 1. That is to say, we need the slope is equal to the derivative evaluated at x equals 1, which in our case is 2 times 1 minus 4, which is negative 2. And even within the limits of my terrible, terrible picture, that slope stinking better be a negative number. And sure enough, it is. So to find the slope, you evaluate the derivative at the given x value. Substitute x equals 1 into the original function, that just finds the y coordinate. Substitute x equals 1 into the derivative, that finds the slope. And now we know where that goes, the negative 2, that's the slope. So let's see if we can finish this the rest of the way out. So we have y minus 4 is equal to, my number is negative 2, and then we have x minus 1. Now, I don't care what the answer book has, I don't care what the internet tells you to write, I don't care what the solution manual has, I don't care what any tutor says to do, it doesn't matter to me, it doesn't matter to me. Anytime you're asked to find the equation of a line, in any course I teach, except for Calc 3, in any course I teach, except Calc 3, any course you teach, if you're asked to find the equation of a line, your answer needs to be in slope-intercept form, slope-intercept form, slope-intercept form, y equals mx plus b, slope-intercept form, if possible. Some lines it's not possible. But if possible, write this in slope-intercept form. So the rest of this, you would hand off to your basic algebra knowledge part of your brain. So this gives us y minus 4 is equal to distribute, that's negative 2x plus 2, add the 4 across, and we get y is equal to negative 2x plus 6. And we have found the equation of the tangent line when x equals 1. Even within the limits of my very, very badly drawn picture, that at least seems reasonable. mx, the slope is negative 2, plus b, the y-intercept is 6 on my terrible, terrible picture. If you were to draw this much more accurately, you would have a much more accurate rendering. The picture is not what counts, it's the computation. We're doing this problem analytically, not graphically. And so, given a function, you should be able to find the derivative. You should be able to find the derivative using the definition of the function. You need to be able to do that. Not just so you can get points on an exam. You need to be able to find the derivative using the definition because you need to know how to find the derivative using the definition. It's an important skill to have. It needs to be in your skill set. You need to practice it so it becomes part of your basic skill set that you know how to do. So there's the derivative. We found that using the definition. And then once you have that derivative, you can use it to find the equation of the line tangent to a curve. Now, this must be given. If this point were not given, then the problem could not be done because you would not know this value. That means you not know this value, you don't know this value, and there are too many things that are not known in the problem. So certain pieces of information must be given. But with those, the derivative is the tool to, number one, find the equation of the tangent line. And then from that, the interpretations spread from there. We will use a derivative to find many, many other things. This is first base.